In the last video we defined equilibrium, and we saw that a general system, a non-linear one, may have different equilibrium points. Obviously it is possible that the system presents only one equilibrium state, but in general it is common that the system presents several different equilibrium points, something that we exemplified somehow with this figure here, this physical system with several equilibrium points. And each one of those equilibrium points belong to one of these three categories we described according to what happens to the system when the equilibrium is disturbed. As we are about to see, each one of these possibilities, each one of these three kinds of behavior we may find when an equilibrium state is disturbed, is defining a different stability category. So in this video we're going to focus on the system under study in basic control courses, that is the LTI systems, the linear time invariant systems. And these systems have an important peculiarity, the fact that they only present one equilibrium state, only one equilibrium. So this situation is not possible in LTI systems because only one of these positions is allowed, and in that sense, by abuse of language, we refer to systems stability. We use the term systems stability. Such term wouldn't make any sense in a nonlinear system with several equilibrium points, because some of them could be stable and some others could be unstable. But in LTI systems, when we can say the system is stable or unstable, when what we actually mean is the only equilibrium point of the system is stable, or the only equilibrium point of the system is unstable. So even though we'll accept the term stability of a system or system's stability, keep in mind what that actually means, because in the future we may come across more complicated systems which will not be suitable for this kind of categorization. Now there's another comment I'd like to make here. Having one equilibrium state, one equilibrium state is not the same thing as having one operating point. An LTI system has only one equilibrium state, but it may present several or even an infinite number of operating points, because operating points are, roughly speaking, translation of the same equilibrium, displacements of the system's only equilibrium to another input-output configuration. Well, we'll define all this on a separated video, but I thought it was worth mentioning here that a linear system can work in different operation points. So that being said, let's give a rigorous definition for stability. Definition: stability. There are several definitions of stability which are equivalent to a certain extent, but given that this course is oriented to input-output, or as we call them, external descriptions, the most appropriate one is the BIBO stability. It's BIBO stability, which stands for bounded input, bounded output stability. So a system is vivo stable. I hope this is pronounced vivo. I don't really know. If all bounded inputs lead to bounded outputs. Lead to bounded outputs. This will be the definition of stability will apply to our LTI systems. So according to this definition, this system here would be stable because bounded inputs produce bounded outputs. Bounded inputs, they are below certain value, produce bounded outputs because they are also below certain value. Whereas this one would be unstable. This one would be unstable because these bounded inputs, they are also bounded here, they're actually the same inputs, produce unbounded outputs, and therefore the system is unstable. And what about this one? What about the last one? Is it stable or unstable? Well, in the case of a pulse, a bounded input is producing a bounded output. This output is bounded. But when the input is a step, which is also bounded, the output becomes unbounded. And that is enough to consider the system unstable. Unstable. According to the given definition. Remember that for a system that in order for a system to be stable, all possible responses to all possible bounded inputs must be bounded. And if one fails to do so, just as in this last case, then the system is considered unstable. However, this last situation is called or is known as marginally stable. And this is rather confusing because the system is not stable, it is unstable, and yet it is called marginally stable because of its special features. But remember, the system is stable. This sounds a little strange now, but hopefully it will make sense when we relate the stability of a system with the position of its poles. Okay, another important remark to make has to do with the fact that stability is a property. It's a property of the system. It is, so to speak, built in. It does not depend on the inputs to the system. This must be crystal clear for you because quite often people get mixed up with this idea. If we have an LTI system, the system is stable or is not, regardless of the inputs, regardless of the forces we apply to the system. Stability is a relation between bounded inputs and the outputs, that whether they are bounded or not. But that doesn't mean that certain inputs can make the system be unstable. The system, like this input may be unbounded, but the system, if it was stable, it keeps being stable. The fact that this output grows beyond bounds is a consequence of the input, not a consequence of this internal property of the system. So remember, stability does not depend on the inputs, but rather it is an intrinsic property of the system. Okay, finally, in this video I'm going to introduce a very important theorem. One that will prove extremely useful in everything related to stability. And the theorem goes as follows. An LTI system is Bibo stable if and only if the integral from 0 to infinity of the absolute value of j of t dt is less than certain finite number. And this is a finite number, which means that it is less than infinity. Or in other words, if this integral converges. So what is this telling us? Simply that that we can find out whether the system is stable or not just by looking at the integral of g of t. That is, at the integral of the absolute value of the impulse response. Remember, this g of t is the impulse response, the response we get from the system when we introduce a unit impulse function. So we take that response of the system, we integrate its absolute value along all positive time, and if such integral converges, if it has a finite solution, then the system is Bibo stable. So, but why is this theorem so important? Why is it worth studying it? The reason is that up until now we had to apply all kinds of inputs to the system in order to know if it was stable, like here, or unstable like here. So we introduce the pulse, the step. But even if we did that with many inputs, we couldn't really be sure that there isn't some other input for which the output is unbounded. And that happened in the last situation. We applied one input for which the output was bounded. Maybe there are some other inputs for which the output is bounded. But there are some inputs like the step for which the output is unbounded, and therefore the system is not stable. The difference is that now we don't need to study all those inputs. Thanks to the theorem, we only need the response of the system to one particular input in order to find whether the system is stable or not. So imagine that the impulse response is this signal here. I don't know, this signal here. Calculating the integral is the same thing as calculating this area, adding up all this area, the area under the signal, assuming that all areas are positive. If such area is finite, then the system, as in this case, then the system is stable. So again, the progress we've made comes from the fact that we need only one response in order to perfectly characterize the stability of a system, and we'll take advantage of that in future videos. But finally, I'd like to point out a further advantage of the application of this theorem, because as we know, the impulse response g of t is the inverse Laplace transform of the transfer function of the system. And remember the reason for that. G of t, when we have a system defined by its transfer function, the output y of s is equal to g of s times the Laplace transform of the input, but the Laplace transform of the impulse response of the impulse function, the delta function, is 1. This is equal to 1. So y of s is equal to g of s in this case, in the case of impulse response. And this allows us to use the partial fraction decomposition on the transfer function, in the way we've already learned. And we do that to get easily g of t that we will introduce in the integral. So this is what we'll do in the next videos with simple systems, and those calculations will guide us to a key relation between stability and the position of the poles.